Hello viewers, we discuss today Lebesgue measure of sets. Measure is an important concept in mathematics, especially in pure mathematics, a part of real analysis. Let's start with the Lebesgue measure. And this concept, Lebesgue measure, of bounded interval either it is open or closed. That means if say AB open or close, open at one ended or in this way or closed, whatever may be, and where it is say where A is less than B. This is a criteria. So in this type of interval, and it is equal to, all of these is equal to its length. Actually, what happens if we considering a real line? In the real line system, if we consider any 2 point, if here it is we can say it is A and B, or better to write here AB in this type of interval, then close point or open points, its length, actually length is given by, from the picture, B minus A. Actually this is called our length. So if we consider any length like this, length of, suppose if we consider an open interval like 0 1 is 1 minus 0, it will be 1. So we can say measure of AB, if we consider as A is less than B, is given by the notation simply M of AB. It will be its length of the interval, that is B minus A, in this way. So easily we can say also say, if somebody measure of like this 0 1, that will be 1 minus 0, that is 1, in this way. Now the question is, why this concept build up? This is the main questions. To get some of the idea, we explain, for further explanation we needed some definition. Let's watch till the end of this video to clear this idea. We apply this idea for a bounded open set. So we needed the definition of bounded open set. So we have to find here measure of a bounded open set, whatever may be the set is, like H say, is denoted by simply measure of H, if we consider H as a bounded open set, then measure of H, and it is equal to, we needed another concept here, how to measure this bounded open set, because we don't have any kind of tools here. So how to find it? The question is this. And if we subdivided this type of bounded set, suppose if the set is, it should be noted here to clear this concept. If we consisting of the set open intervals, if we consider like this 0, 3, and it is clear that 0, 3 will be subdivided as 0, 1, union, if it is as 1, 2, union as 2, 3, and we see here all are disjoint as 0, 1, intersection 1, 2, intersection 2, 3, that is empty. So 0, 1, 1, 2 and 2, 3 are disjoint open interval. But union of these three getting 0, 3. So if we measure this element, we needed here of the open interval like this, or open set. They may have the countable family of disjoint open interval like this, 1, 2, 3. All are countable family of disjoint open interval, and we needed here to measure all of them each. Like this, if we are taking measure of this, if we extend it, m of as m of 0, 3, we may extend it as m of 0, 1 plus m of 0, 1, 2 plus m of 2, 3, like this. And if we are wholesale finding this result, 0 minus 1 plus minus 0 plus 2 minus 1 plus 3 minus 2, so that will be 1 plus 1 plus 1, that will be 3. So it is clear length of this interval is also 3. We can explain in this way also. But in abroad definition, if we are looking at this figure like this open set cap H, we don't know the picture of H actually. We don't know here. Then how to adjust this type of problem and how to measure this type of set? So here we needed the concept of countable disjoint open interval, that is, this set is subdivided different type of countable family of disjoint open interval. That's why like this we can find here finite number of these, but we don't know here. We may assume it may infinite. We don't know what happens if this set is infinite. Then we are going to define it. Image is equal to summation like this. Here also summation. Sum means addition of these three. Finite and its extent up to infinity. Suppose n is 1 to up to infinity. Measure of all subdivided part. That's why it is an also interval concept we have to take here. Delta n, suppose, where this open set H is the union of delta n equals to 1 to up to infinity, and this delta n is a countable family of disjoint open intervals. This is our concept. They are the countable family of disjoint open intervals. Here also doing same things. That's a countable family, disjoint open interval, because if we are doing this open interval, these three are disjoint. They are disjoint open interval and countable 1 to 3. And here it is countably infinite cases 1 to up to infinity. And here it is countably finite, only 3 stage. Now since H is assumed to be bounded, and since it is bounded, so it may assume it's finite, so we have this summation, that measure n equals to 1 to up to infinity, measure of delta n is finite, that is less than infinity. And as measure of an open interval is positive, then we have, it is clear, measure of H must be positive, and if not positive, if not, so then it must be empty, that is measure of H must be 0. So we can't find any negative measure, it must be positive. It is not possible to find any negative measure. Now one question arises, why we have required this type of concept. Actually, main application parts of this measure in the set theory used in probability theory in abroad senses. But now here we study only the part of Lebesgue measure. So in this way we get glimpses of idea of measure. In my next videos we get some concept about few theorems in measure, but I don't mention it. If I mention, this theory is too longer. That's why in my next video I will discuss few important theorems in Lebesgue measure. If you like this video, like it, share it, and always subscribe the channel and press the bell icon to get all of my notifications to my video. Thanks for watching.